The mission came and went with little fanfare. And if you ask the average person on the street, it's likely they'd never even heard of it. But in the scientific community, in the SETI community more specifically, this singular mission was perhaps the most significant science mission in NASA's history, and arguably one of the most profound space missions in all human history. I'm speaking here of the Kepler Space Telescope, which made the truly astounding discovery that essentially planets are everywhere, that indeed they likely outnumber the stars in our own galaxy. We now know that what you are really seeing on a clear, dark, starry night are not thousands of stars, but in fact, thousands of solar systems. Kepler also taught us that not only are planets ubiquitous, but approximately 20% of them are rocky, Earth-like planets in the habitable zone of their host star. The implications of this are astonishing and include the prospect that in the Milky Way galaxy alone, there are likely tens of billions, that's billions with a B, of potentially habitable worlds. This knowledge has certainly transformed the search for extraterrestrial intelligence, or SETI, into one of the most compelling research endeavors of our time. Roll forward in time, and we have the follow-on mission to Kepler called TESS for the Transiting Exoplanet Survey Satellite. Launched 4 years ago in April of 2018, TESS is surveying the entire sky, looking at relatively nearby star systems to discover new exoplanets. It's already added hundreds of new worlds to the thousands of known planets already discovered and confirmed by Kepler and other programs. Many scientists, including our guests this evening, are interested in looking more closely at the candidate planets in the TESS database to see if they might not only be potentially habitable, but indeed to see if they might reveal so-called technosignatures that would suggest the presence of advanced technological civilizations. This is extremely exciting research. Our guest will be introduced this evening by Franck Marchese, senior astronomer at the SETI Institute and the moderator for today's discussion. And if you look closely at the background behind one of tonight's guests, you'll see this big image of a beautiful actress from the 1940s and 50s, whose name is Hedy Lamarr. And her image is on the wall of one of our conference rooms at the SETI Institute. And she was nominated to have a conference room in her name by one of our trustees who admired her work, not as an actress, but as an inventor. And some of her patents are at the heart of technologies we take for granted today, including Bluetooth and Wi-Fi. So you'll see one of our guests sitting there in front of this large image of Hedy Lamarr, who we pay tribute to at our conference room in the SETI Institute. So good evening, ladies and gentlemen, and SETI Institute friends the world over. Thanks for joining us for tonight's SETI Talk, the TESS Mission, a search for ET. My name's Bill Diamond, and I'm the CEO of the SETI Institute. For our regular SETI Talks attendees and new guests alike, let me remind you that you can post questions using the Q&A feature at the bottom of your screen, and we'll do our best to address as many as we can at the end of the panel discussion. I also want to remind you that we love to know where you're joining us from, so please use the chat function to tell us where you are on or perhaps off our home planet. Our SETI Talks lecture series is a production of the SETI Institute in Mountain View, California, and it's made possible by the generous support of people like you. You can learn how to get involved in our mission, support our work, or sign up for our weekly newsletter called Journey online at www.seti.org. Today's talk is actually sponsored by the many donors and friends of the Institute who participated in our own Giving Day, which was back in April earlier this year. Their gift to us is a gift for all of you, and we're very grateful for their support. If you'd like to personally sponsor a SETI Talk or learn more about how to support our work, visit us again at SETI.org or contact us by email at info@SETI.org. Finally, before turning the podium over to Frank, let me tell you briefly about our next SETI Talk, which is going to be on June 29th at noon Pacific time, where we're going to host an Ask the Institute Anything session. And that's going to feature many of our own research scientists. It's really going to be fun. And you could be the star of the show with your insightful and imaginative questions. And, you know, for those of you who are familiar with Reddit AMA, it's going to be that sort of fun format of questions coming in and answers going out and opinions and responses from a number of our scientists. So don't miss that fun event on June 29th. And with that, it's time to turn the proceedings over to Franck for a survey discussion on the search for ET using data from NASA's TESS mission. Franck?
Thank you very much, Bill. Thank you. And hello, everybody. We have more than 300 people watching us right now. So yeah, today we are going to talk about how the TESS mission could be useful to find technosignature, intelligent technological civilization. And for this, we invited two scientists. So let me introduce you first. One of the youngest scientists we have at the SETI Institute, Noah Franz. Hello, Noah. How are you?
I'm good. How are you?
I'm good. So where you are calling us from?
I'm calling in from upstate New York.
Okay, so Noah is a junior physics and data science major at Siena College, which is a small liberal arts college in upstate New York. And Noah was lucky because he worked in the past summer as an intern at the Berkeley City Group under the supervision of Steve Croft. And he performed a search for radio technosignature using the Green Band telescope in West Virginia. So today you are going to tell us a bit about your work and some of the results you got. And I know it's going to interest a lot of our viewers. And closest to me, I'm guessing, Anne-Marie Cody. Hello, Anne-Marie. How are you?
Hello. Good evening.
Good evening. So you, Bill stole the thunder already. You are at the new SETI Institute headquarters in the Lamar room. That's correct. And
Yes.
So Anne-Marie is a scientist at the SETI Institute. First of all, she's a principal investigator. She has also worked at NASA Ames as part of the postdoctoral program over there, and working on the Kepler and K2 missions. Anne-Marie is known for work to explore the diversity of variability behavior among stars. She has kids as well, so she knows that behavior is extremely important, even among stars. She has studied a newborn star and a planet-forming disk. But today she's going to tell us a bit about her work on the search for megastructures around the TESS, using the TESS mission around stars which are not that far away from us. So Anne-Marie, I know that you have prepared a few slides for us, so tell us a bit more about your work, please.
Great. Let me share my screen briefly. Okay, thank you for the introduction. Frank and Bill mentioned searches for technosignatures, our desire to find signs of advanced life elsewhere in the galaxy. And we have been interested in this question for a very long time, but now we're especially interested because of all the exoplanets that we know are out there. So there is currently a flurry of scientific activity aimed at studying those planets, their atmospheres, looking for signs of life, biosignatures, which may indicate more simpler life forms, molecules, and so forth. And at the SETI Institute and beyond, for decades, we've been looking for signs of more advanced intelligence using radio antennas, and more recently looking for optical communications in the form of laser pulses. What I'm going to tell you about tonight is a relatively new area. We're using the Transiting Exoplanet Survey Satellite, or TESS for short, NASA's mission, to look for signatures of large structures orbiting around other stars and blocking out their light. Why might this be possible? Why would we expect this? For a while, scientists have been contemplating what happens when a civilization becomes very advanced beyond our capabilities currently on Earth. And it is thought, it's just hypothetical at this point since we haven't discovered anything, but that we or other civilizations could eventually need to harness more energy than is available on our home planet. And at that point, we might actually want to build structures around a star to gather all that energy and maybe send it back to the planet. Those structures would be potentially large. You may have heard of the concept of Dyson spheres or Dyson swarms. And they could potentially block out the light of some of that star, which is important to us because we could then observe it here on Earth. I'll go into more detail in this about this as we discuss, but the brief idea is that if you have a series of panels or other large objects and they're in orbit around a star, the star's brightness over time, which you're seeing a little schematic of here, would appear to undergo fading events. So you see the starlight and then something passes in front and then it goes faint for a little bit. Could we actually see this? The exciting thing that we're here to talk about tonight is yes. And it is all in thanks to NASA's TESS mission. This is a schematic of the telescope, which is out there in space with 4 cameras that stare at the sky. They're doing it as we speak. And it has been looking at roughly 100 million stars across almost the entire sky. It's measuring their minuscule brightness changes over time. And it's in that data set that, that I and numerous other scientists who I work with, thanks to funding from NASA, are now mining that data set, looking for brightness changes that may be due to some kind of megastructure in orbit around them. All right, thank you.
Thank you. Thank you for this introduction. And Noah, so your work has been mostly in radio, and also I know that you have prepared a few slides, so please go ahead.
Okay. Can you see them?
Yes.
All right. Thank you, Frank. So I'm going to be telling you about a search for technosignatures in test candidates. And so technosignatures are any sign of extraterrestrial intelligence. But the one I was looking for in particular was radio signals that were possibly sent towards Earth. And so this right here is a sky map. And it's, if you imagine you looked up at the entire sky and it unfurled it so that you were looking at the entire sky all at once. That's what this is, and it's just in astronomical coordinates. And so this gray shaded region is the Green Bank Telescope observing area. And all of these blue dots are the test targets of interest, or any of the test targets that they've thought could be candidates for exoplanets. And then these red X's plotted on top are the these are the targets that I used for my project last summer. And they are any of the test targets that were in transit during their Green Bank Telescope observation. And this is a really interesting time to look at test candidates, because during this time, extraterrestrial life on these exoplanets that may exist on these exoplanets may think, oh, we could send a signal while we're transiting and know that we could observe them. And so I collected all of my data with the Green Bank Telescope. And so that's pictured here. And it's a very large radio telescope located in West Virginia. It's 100 meters in diameter, which is huge. And for scale, you can see an adult human, or I mean, you can't really see an adult human right here. And like, it's like, they're tiny compared to this massive structure. And so how it works is radio waves come in from space. They reflect off of the main receiver, our main dish right here, bounce up to the sub-reflector and then into a receiver antenna here, where the data is collected and then processed. And so for this project, I ended up collecting 21 terabytes of data, which is a massive amount, like something I could definitely not even come close to storing on my laptop. And all of this data is in both is at different frequencies depending on the receiver used. And for each observation, we can focus on this left plot here. Data was taken on both on and off targets, which means that an on target for this observation was TIC 409183335. That was like the target of interest that we actually were like trying to look at. And then the off targets were these other targets that start with HIP here. These are just other sources in the Hipparchus catalog that were near in like close in the sky to the on target. So how an observation goes is it's a 5-minute observation of an on target, then a 5-minute observation of off target, then on target, a different off target, then the on target again, and then the third different off target. In this way, we can eliminate a lot of the radio frequency interference, or just any interference coming from things like satellites, or let's see, like phones on the ground, things like this giant telescope could pick up. This way we can eliminate those as technosignatures, because we can say technosignatures must only be present in the on observation. So it would be a present here, here, and then here again. But any other interference would be present throughout the entire observation. And so these were two signals of interest that I found in the data. This first one on the left, I found interesting because like there is some signal present in just the on observations, but there's also some present in this off observation, and the signal is pretty wide. It's not like the expected narrow signal across the observation. And so this can be eliminated as a technosignature. Also, it's at a frequency range we typically see aeronautical radar. So it's possible it's either a satellite signal or something with aeronautical radar. And like it's definitely not a technosignature. This one on the right, here, this, you can see there's a good narrow signal all the way through. And it's interesting because it bends as it goes through. But you also see that as satellites. And since the signal is present in both the on and off observations, it's definitely not a technosignature. So what's next? Well, two interesting projects that could be follow-ups for this are looking at when an exoplanet goes, instead of in front of its star, but behind the star, we could see if if a signal disappears coming from the exoplanet. Or another project could be looking if a exoplanet begins its transit and then a signal turns on. It could have a constant signal and then the signal turns off once it ends its transit. This would be clear that like extraterrestrial intelligence like thinks we may be watching. Yeah, thank you.
Thank you very much to both of you. Thank you, Noah, for giving us a summary of your observations and the data collection for this with the Green Bank telescope. I have a question. I have plenty of questions. So I'm just gonna remind our viewers that we have a conversation for 30 minutes, and then we're gonna take some of their questions as well. And we recommend you post your question in the Q&A section here. And some researcher in the back, Rebecca and Beth, will basically select some of the questions later on. So we will take the time to answer to the one which are the most popular. Anne-Marie, you the astronomer here, I would like you to give us some, without flooding us with too many numbers, please give us a bit more information about the TESS mission itself. How many planets this mission has discovered, how long it's been in operation. So you can give us an idea of the difficulty here with your program.
Yeah, so the TESS mission, as I believe was mentioned earlier, is basically a follow-on to NASA's Kepler mission, both of which were designed to find exoplanets in orbit around other stars. That was the primary goal, using this transit method. So basically looking for a small dimming of the star as a planet passes through our line of sight. These are very small events, like a 1% change in the light, but these space telescopes are very good at that. So with Kepler, we were able to identify several thousand exoplanets. The main issue was that most of these were around not particularly bright stars, which made it harder for astronomers to follow them up. So the whole idea behind having a whole nother mission, the TESS mission, was to look at the brightest stars on the sky and all over the sky. I should have said Kepler just looked at initially one patch and then a few other patches in its extended mission. So with TESS, we're now harvesting planets at a pretty fast clip. We should say these transiting objects of interest is basically a planet candidate which has not yet been fully verified. So there are over 5,000 candidates already found with TESS. I believe a small fraction, around a couple hundred, have been confirmed, but a lot of work is underway to rule out scenarios that can kind of pretend to be planets. Like if there's another star in orbit around it, we can get what we call false positive scenarios. So TESS was very much founded to look for planets, but as it turns out, it's really good at doing anything that has to do with monitoring the brightness of stars and other things out in space.
Okay, just one number I would like to get from you is Kepler has been observing star systems which are far away from us. What is the typical distance of the TESS planetary system?
Well, that's a good question. Well, many of the planets being found with TESS are around stars smaller than the sun, little red stars called M dwarfs. And those can be anywhere from like 10 light years out to, or even less than 10 light years out to, a few tens of light years. But I would say it's sensitive to things even out to 100, 300 light years. It just depends on how faint a star you're willing to look at. But yeah.
So I remind our viewers that even 300 light years seems to be a gigantic number. It's in fact our close surrounding, because our galaxy is typically 100,000, 200,000 light years in diameter. So with TESS, we are really looking at the close vicinity of our star system, our sun. Okay, Noah, so you show us that with the Green Bank telescope, you have been listening to star system discovered with TESS, TOIs, let's call them like that. So how many of them did you listen to?
Yeah, so I'm happy you asked this because I meant to mention it. So I was listening to 61 TOIs, and yeah, I mean, that seems like a small number, especially compared to the like 5,000 that Anne-Marie just mentioned of targets that TESS has observed. But this is just like a subset, because I looked at data that had been previously collected by Breakthrough Listen, and this data, I essentially searched for targets that were observed during their transit. And this is like this can be a very small fraction of the orbit. Like the time that a planet is in transit, an exoplanet is in transit, is very small compared to its entire orbit. So this like 61 out of however many that Breakthrough Listen observed at the time is actually like a decent fraction.
Okay, so why, just remind us why you decided to observe them when they are in transit?
Yeah, so I decided to observe them in transit for a couple of reasons. First, extraterrestrial intelligence on the exoplanets may like assume we are watching them while they're in transit. And so they could send a signal while they're in transit, which means this is like a favorable time that we would observe them. Also, it's interesting because like, say their extraterrestrial intelligence exists on these exoplanets and is sending out a signal in the plane of their orbit. This is where we would observe them. And this could not be like necessarily towards Earth, but just to like some other mission they've sent to space. We could possibly observe some of like the radio leakage from that as well. Just, so again, making it more of like a favorable time. Yeah.
So the scenario is that, let's imagine there is a civilization on one of these TOI. Because we are very noisy in radio, or maybe because they invented telescopes capable of imaging Earth, they basically wait to be in transit for us to send a signal telling us we are here.
Yeah, exactly.
Okay.
Yeah.
All right. Interesting. So, Anne-Marie, before telling us the big reveal, did you find anything? Can you explain to us concretely how you do this data analysis?
Yes. So basically, the TESS satellite, it has several cameras which will stare at a subset of these 100 million stars for almost a month at a time, and it's basically taking repeated pictures. It used to do it every 30 minutes. Now it actually does it more often. And our job as astronomers is to take these images of stars and convert them into measurements of the brightness of each star, which is called a light curve. And this is a common thing to do, even just to look for planets, right? But we are looking for brightness behavior of these stars that are not planets, that are basically either deeper dips indicating giant structures, or just something really strange. So we're looking for what we call anomalous variability. And as you might imagine, it's really hard to sit at a computer and stare at, tens of millions of things. Like, I don't have time for that. So we have to harness our software and machine learning, artificial intelligence capabilities for that. And we're actually using techniques similar to the fraud detection that might be, it might alert you to someone having stolen your credit card information or something. Basically, the star is, the brightness is kind of going along normally, and all of a sudden it drops down in a way you didn't expect. So we're trying to pick out automatically that kind of behavior. And out of that, we still get like 1 million potential candidates, which we then have to weed through and get our eyeballs on. So we've certainly found some odd things. The spoiler, of course, is that most of the odd things have natural explanations or are something to do with the telescope and not even the star.
Okay. And let's go. We're gonna go back to the odd things, of course. But Noah, you in this, while listening to these 61 TOIs, so you mentioned the detection of a satellite passing by and some weird signal. How do you do this? Do you also look at the data? Do you look at the data by eyes? Do you did you build a software to help you? How does this concretely done, in fact?
Yeah, so I used this software that has already been written, and it's called SETI. And SETI just essentially looks through these observations, the breakthrough listen observations, for signals that are present in the on observations and not in the off observations. But of course, there's some signals still get through from satellites, from local local interference, stuff like that. And so then you take the stuff that SETI says could be a technosignature, and you like, I looked at it and I said, okay, could this be a technosignature? And going through all of them, it was like the two I showed in my slides, like there were some weird looking ones, but none of them did look like a true technosignature, or at least what we think a true technosignature would look like.
Okay, so who decides this, Noah? Did you, when you found those weird signals, did you bring this up to Steve and the team gather around the table and try to find how do you do this?
So I mean, yeah, essentially, like I would find a weird one and I'd either show it to an intern sitting next to me and we'd talk about it for a second, or I'd send it to Steve, who was my mentor for the summer, and he'd be like, no, it's this satellite, or it's this, it could be like this RFI, or it isn't a technosignature for this reason. And usually it would have to first get past me. We had a ton of signals that got passed through SETI, but it would have to, I first screened through them and then I'd see like, oh, are any of these actually good? And then once I thought one of them could be, I got really excited for a second and then soon realized it probably wasn't.
So basically Steve has been killing the dream every time, right? He was like, okay, that's not it. Go back to your computer. That's not it. Okay. So Anne-Marie, you mentioned some weird things in the TESS database. The first thing that comes in my mind when you say weird transit is, of course, the Tabby star that excited a lot of people doing when Kepler was observing it, of course. So did you see anything like that? Do you have a paper in preparation describing some of those variable transits?
Yeah, we have a paper in the early stages, but we have not yet found an analog of Tabby star, otherwise known as Voyagian star. This is something that was discovered with Kepler and had kind of intermittent deep brightness plunges. And that was actually one of the motivations for this search, because initially nobody could figure out why this star was fading. Now, I come from a background of studying very young stars, which still have a lot of planet-forming material swirling around them. So those show fading events with natural explanations. Basically, the dust sometimes gets in the way of our view of the star and it appears to fade. So I was actually used to seeing that kind of thing, but there was no such dust known around Voyager's star. So I think there probably is dust there. It's just really hard to see. It's kind of the consensus now. But I've gotten excited at times too. We found something with a couple fading events. It's clearly, it's not quite symmetric like a transit. And we have an extensive vetting process, which usually kills my excitement fairly quickly. A lot of what we're seeing is artificial. So the TESS telescope is not really too far from Earth in outer space. And there's a lot of light bouncing off Earth from the sun. And sometimes it sneaks into the side of the telescope's detector and it creates kind of a wavering background. And if we don't remove that background from the stars properly, then we get some dips. The tip off though is usually that we find something interesting. Our first task is to go look at the stars that are near it. And we know it's a red flag if there are several stars next to each other, all showing the same weird things. So we found a lot of that. We found some of these young stars, which I'm interested in for other reasons. And we find a whole lot of eclipsing binary systems, 2 stars in orbit around each other, and some of which have like streams of gas going between each other that creates a kind of strange shape when they do those eclipses. So we have found a lot. We are still very much sifting through the data. So there may be more to come.
Yeah, there is. I mean, you seem to be redoing the analysis. That's why I understand properly. You regenerate yourself the light curve.
So the thing is, they were not generated in the first place. One sort of subtlety of the TESS mission is that it has several observing modes, and it takes these giant images of the entire field of view. It used to be every 30 minutes. And but at the same time, there are sort of some favorite stars, which astronomers pick, especially for the search for planets. And those get just a little sort of cutout image downloaded of the star, and the mission will create light curves of those objects, but they don't create light curves for the 100 million or so stars that are all across the sky. So we had to go and do that first, and then understand the properties of that data and what kind of effects might have snuck in there that's not astrophysical.
Yeah, so the great thing here is that even if you don't find a technosignature or a megastructure, you're still now getting more scientific data that could be useful for other type of research. Like you mentioned, the study of young stars, the variability, seismology, for instance, to understand their structure, etc. So that's the search for SETI is useful because it provides as well scientific information, and you're processing data that would not have been processed, in fact.
That's right. I
That's
mean,
great.
we're basically, as part of our search, a byproduct is just huge lists of all kinds of interesting variable stars that are out there.
Okay, so I have a question which is not about science, but let's start with you, Noah. I mean, you're working for SETI project. I mean, I'm sure when you mention this to your friends or your family, they must be excited about it. How did you start being interested by SETI? What happened? What's the story? How a student like you get into the research like you describe it?
Yeah, so I kind of purposefully stumbled into it, if that makes sense. So I applied for an internship with Berkeley SETI. It's funded by the NSF, and I ended up getting accepted to it. And I was like, this is a cool, awesome project, awesome opportunity. why don't I try it out for a summer? And I started working on it, and it was really, really awesome. And so I've stuck with it. Yeah.
All right. So is there any books, series, sci-fi things that inspire you to work for SETI? Is that something that you?
Not really, honestly. No, I honestly kind of just stumbled into it, and it's now I kind of like think it's a really cool thing to work on. So.
All right. And you, Anne-Marie, I mean, you are a senior astronomer at the SETI Institute. So you've been working on study of stars. You have a lot of papers related to this. So how SETI came out? How they suddenly you kind of switched to all this project?
Yeah, well, I guess I could use Noah's words and say I also sort of stumbled into it. I mean, I've always had my eye on the big questions. And when I was growing up, I heard in the news about all these exoplanets when they were first discovered. And by complete coincidence, I actually grew up in a little town on the East Coast where, looking back now, one of the first exoplanets was actually discovered at an observatory there. And so it was like big news in my little town. And so all these questions, of course, have arisen. Now we know of 5,000 confirmed planets, but there's probably billions in our own galaxy. And I'm just always been drawn to these questions of what's out there. Research-wise, I had earlier and still am addressing sort of where do things come from, which is a slightly different question. How are planets born? We find them, but they're around older stars. Like, where were they initially? How did they come to get there? And so I saw all this crazy variability of the planet forming material around stars. And when Boyagin's star was discovered, I was like, oh, that looks like some familiar type thing. And I just got kind of drawn in, and I'd been working with these space telescopes for a while and started to think about, I was also affiliated with the SETI Institute prior to getting into this area of research. So as I started to meet people at the SETI Institute, I got really excited about what they were doing and thinking, what can I do with my kind of complementary skill set that would add to the search?
Okay. And do you read science fiction? Do you?
I'm going to be lame here. But, when I was growing up, it was like there were some portion of my friends that were very into Star Trek, and it was considered sort of the nerdy thing to do, and it was almost embarrassing. So I was kind of driven like toward the science, but with a real basis in the observations, like reality. And I felt like science fiction was a little too out there for me. Of course, now I've changed my mind, but I don't have a whole lot of spare time to read. But I've been more involved on sort of the creative arts end of things. And the SETI Institute, some of the audience may know, has an artist in residence program. I've really enjoyed talking with these artists and writers, just thinking about all the possibilities of what could be out there and what form it might take. So that's really been my most recent inspiration.
All right, thank you. So I have two more questions. This is the clue from Rebecca and Beth to start looking at the questions from the audience. So we're gonna ask that I'm gonna ask in a few minutes. So Anne-Marie, this work is still in progress. TESS is still taking data. Right now, at the moment I'm talking to you, there is data coming from Earth, from TESS. I can bet that because I see in the antenna, DSN network is basically collecting that TESS data almost continuously. So it's possible that in the next days, weeks, months, you find something. So how are you gonna announce this? How are you gonna basically go from the excitement of finding a Dyson sphere or something weird around a star to validating, to announcing that to the public? Do you have a scenario already?
Yes, well, obviously it's a very serious thing. And so for that reason, we have to have quite extensive vetting procedures in place. We have to think about all the possible causes for such a signal that are not alien civilizations. And so we go through that vetting process initially with the test data. But then we have some sort of a time promised to us on ground-based telescopes, which we can use to look at stars of interest at different wavelengths than the TESS detectors are. They kind of look at a broad spectrum of light, whereas we can look at red, blue, et cetera, from these ground-based telescopes. And so the first thing we would ask is, if there's something blocking the starlight, is it a solid structure? In which case, we should see these events. They should look the same in all different colored filters. If they don't, which was the case with Boyajian star, then we might conclude there's something there, but it's more likely to be dust. So we're going to have to go through that. We would also pass our targets of interest off to radio researchers like NOAA and see if there's signals coming from them. If we pass all these tests, we're going to do the standard scientific procedure of writing things up for a journal and having it be reviewed by other scientists who might also think of reasons why this might not be the case. There's a series of roadblocks that it has to get through within the scientific community. Ultimately, if a signal actually passed all those roadblocks and were approved as a bona fide signal or a sign of a technosignature from alien technology, then I think it would become more of a political issue. It would have to deal with in the greater astronomical community. And people tend to think that there's this culture of hiding alien signals. There's always these conspiracy theories, but in reality, the scientific community strives to make discoveries public pretty quickly, as soon as these vetting processes are done. So you would be hearing about it.
Okay. Thank you. Thank you for the description of the process. What about you, Noah? Do you know if there is a detection of technosignatures in the future? I mean, I'm assuming that this new program is going to continue, or probably the Green Bank telescope is taking data at the moment. So what's the process in the case of radio astronomy?
It is very similar to what Anne-Marie said. So we, like I said, say Turbo SETI comes back with some signal that we decide could possibly be a technosignature. Then we start digging through the data and just going through this vetting process, seeing could it be from anything else, checking satellite passes near the telescope, seeing could it be from a satellite, could it be from some local interference, was it present in other radio observations that day? That could be interesting because maybe there's someone forgot to turn off their cell phone near the telescope. Just thinking of things like that, and then like Anne-Marie said, writing it up, getting other researchers to think about this as well before it actually becomes announced to the public is very important, because maybe we missed something. Yeah.
Okay.
And then eventually just getting it out there, because that'd be huge. Yeah.
Yeah, that will be huge, definitely. So this, as I mentioned, the survey is going to continue, but there is new facilities coming online. Maybe you can tell us a bit, Noah, if you are inclined. Tell us what's the field of radio astronomy at the moment. Is there any new instruments coming online that could be useful for your research?
I don't know of any new instruments, but I know, other than the Green Bank telescope, Breakthrough Listen, Berkeley SETI, they're all working also with the Allen Telescope Array in Northern California, which is an array of smaller radio telescopes, instead of just one big one like the Green Bank telescope. There's also the Parkes telescope in Australia, which is similar to the Green Bank telescope, and it's just a large single dish telescope. And then also the LOFAR telescope in Ireland.
Okay.
That one is a new one. Yeah, it's coming soon, I think, to being used with Breakthrough Listen. Yeah. So
this program is basically using additional telescope, not only the Green Bank telescopes, to do the same type of research on additional TOIs. What about you, Anne-Marie? Any plan in the future to use more space telescopes?
Well, the survey that TESS is performing is pretty comprehensive in terms of the number of stars that it's looking at. So for us, I would say the main aim would be to use other facilities to perform necessary follow-up for anything interesting that we find. Of course, we would certainly welcome it if there were a similar space telescope or several telescopes that would look at different wavelengths simultaneously. That would help us figure out in real time without some of that follow-up, whether a signal is likely to become coming from megastructures. I'm not aware of such a mission planned yet, but it would be very interesting. But certainly there are newly launched NASA missions like the James Webb Space Telescope, which are designed more so to do follow-up of single objects rather than look at millions at a time. So that could potentially be used to look at stars with maybe planets if we find something interesting coming from that star, to analyze the signal at another wavelength.
Okay, so we have a lot of questions from our audience here, and we are going to try to answer as many as possible without staying here until 9 p.m. So let me start with the first one. I think this one is for you, Anne-Marie. Could you explain how you tell the difference between the transiting exoplanet and the ordinary sunspot, a star spot, or an alien megastructure?
Yes. So when we look at the brightness of stars over time, we get these so-called light curves. They all kind of, after you've stared at a few thousand, you start to notice they have different shapes. So the signature of an exoplanet is typically the star's brightness is pretty steady. Then it drops by maybe 1% or so, and it has kind of a flat bottom, a square shaped bottom. And that's because the planet is roughly opaque, and then it gets bright again. Star spots tend to have more smooth variations, kind of like a sinusoidal wave. Although it doesn't necessarily have to be. You can have multiple star spots and kind of waves beating against each other. Now, I should say we don't exactly know what we're looking for in terms of megastructures. I mean, we're kind of leaving it up to our software machinery to tell us what is strange, but we have done some kind of simulations where we put imaginary giant shapes in orbit around other stars, and we simulate what the light curve would look like. And typically we can create pretty deep dips, so deeper than you would get from a planetary transit. And you can get those as well if you have a stellar binary system that's eclipsing. But the difference is that when you have two stars, they're both shining, whereas we don't think that panels shine. So you have a bright star and a dark panel passing in front. So with a star, two stars eclipsing kind of system, you get two dips of unequal depths in the light curve. With a megastructure, you only get one, and it might be a different shape. Like if you have, say, a giant triangle going across in front of the star. So we spend a lot of time looking at morphology of lightness of light variations over time.
Okay, thank you. This is a very interesting question. But first, Noah, could you tell us what kind of radio signal can be detected? But I'm asking questions specifically of, are we talking about an extremely energetic radar? How far can it be? Do you have some numbers to give us an idea? For instance, if we have an Arecibo at 10 light years, will you be able to detect this?
I'm going to be completely honest. I don't really know. I would say, I think with Arecibo, I'm honestly not sure. I don't want to give like false information here.
Okay.
Yeah, sorry.
No problem, no problem. The question I have also, if, that's for Anne-Marie, if an intelligent species is observing us right now, will they be able to detect a technosignature? I mean, we have things flying around Earth. We have things flying around the sun that we made. Is that possible to detect those?
You mean like satellites in orbit around the Earth, that kind
Yes,
of thing?
for instance.
they're so small that with our technology, I don't think that that would be currently possible because, with NASA's space telescopes, it's hard even to detect the entire planet Earth. Now, if you have some giant planet and huge satellites around it, could you detect a belt around it? It may be possible, but there would also be some scenarios to rule out, like, is this just a ringed planet with some natural rubble going around it? But in general, the signal that planets create when they pass in front of their host star is already quite small. I mean, a Jupiter-sized planet is like a 1% decrement in brightness. Earth is some orders of magnitude below that, which is why we need these sensitive space telescopes. So if it's hard to detect something the size of Earth, and then you see a transit, and then you want to see other little things kind of following after our planet, it would be difficult. Suffice it to say. So we're looking for things that would probably be a bit closer in and large, even like planetary scale size, but then they can't be so close into the host star that the material is actually melting, because then they couldn't be there.
Okay. One more question. There is a new trend in astronomy called citizen science, citizen astronomy. Is there something that a citizen astronomer could do to help the search for technosignatures or the search for megastructure? And Mary, you want to start this one, or Noah?
Well, I'll say one thing, and then I have two things to say, but the first, and Noah can elaborate on, is that I'm kind of dating myself here, but when I was growing up and I would sit at the computer doing my homework, and I would have like essays that I would have to write, and I would have writer's block, and the screensaver would come on the computer. This project started at Berkeley called SETI at Home would come on, and my computer would churn away on SETI radio data as I sat there not doing my homework. So that's kind of the way I see early citizen science going on. I think Noah probably is aware of more modern projects going on in the radio domain. And I can say in a minute what we have in mind for megastructures. We haven't started anything yet, though.
Yeah, so the first thing that popped in my mind was also SETI at Home. And I honestly don't know. I don't know how active it still is, but I mean, I think like my thing would be just get involved. Like, I mean, you could reach out to any of us about how you could help specifically, with like whatever skills you have. I'm sure there's stuff that you could do. Okay,
that's a good advice. Just send an email to SETI Institute, and we will find a volunteer job for you. No matter what you do, videos, computer analysis. There is always something that a SETI researcher would like to find someone to do. Definitely. Anne-Marie, go ahead.
I was going to say you should also maybe mention the Zooniverse projects for folks that are unaware of those. There's
yes,
a variety of citizen science areas that you can get involved in. We don't have one specifically for megastructures, but we've contemplated it takes a lot of infrastructure and setting up training to actually show people how to look and what they're looking for. But such a thing has been done for exoplanets. So you can go to the planethunters.org website if you want to look through real life test data for planets, not megastructures. But in doing so, you'll have the opportunity to just stare at a lot of data and see what else is out there.
Okay. Okay, so this is a very vague question, but maybe one of you will take the time. Can you define what is a true technosignature? What will be the content? What will look like the signal?
I think the best answer is no one really honestly knows. I mean, there's things like we can, like Anne-Marie was talking about, like how you guys have simulated what a megastructure would look like. And I know like for radio astronomy, like we think like a technosignature would look like a signal that is coming just from our target. So just present in the on-off observations, not present in the on-off observations. And of course, like we've simulated this as well. And we can say like, this is what we think it should be, but I don't think we actually know. And I don't know if Anne-Marie, you want to elaborate, but.
Yeah, well, broadly speaking, there are whole different classes of technosignatures. And in general, it's, I think, anything that a civilization at least as advanced as us could generate that would not otherwise be present on a planet. So, I mean, it could be communication technology, electromagnetic radiation that's coming away from the planet that we can see. Megastructures are more of sort of an engineering feat, or some astronomers are actually looking for signs of industrial pollution in atmospheres. So that's a whole nother set of things. So it depends on what you're looking for, but basically the byproduct of some beings out there that know at least as much as we do about how to manipulate their planet, maybe even their whole solar system.
Okay. Another question for you, Anne-Marie. You talk about space telescopes, TESS, but do you know if there is any survey involving ground-based telescopes specifically for the search, the type of search we're doing?
Technosignatures.
For the search for megastructures.
I'm not actually aware of any. I think most of the ground-based surveys are focused on finding planets and looking at variable stars. So they are going to be useful for us, and also looking for farther off explosions in other galaxies, for example. So there are a number of those, and we're actually planning to leverage some of that data. Again, it's not intended for our purpose, but some of it goes back quite a few years. So if we find something interesting, we're going to look at the historical data. And the great thing about these small ground-based telescopes is they tend to have fairly large fields of view on the sky. They're not just looking at one little star at a time. So they're pretty big databases, and many of them are public. So, but I don't know. I don't know of any that are specifically looking for megastructures. That'd be fun.
Okay. Okay, so I'm looking at my list of questions here. Oh, this one's we've been talking a lot about machine learning, artificial intelligence at the SETI Institute with the FDL program, of course. So could you tell us, both of you, if there is any use of machine learning and how you use machine learning in the search for technosignatures or megastructure? Noah, do you want to start this?
Yeah, I can. So this is not what I focused on at all, but I know that machine learning is being used to search for radio signals, especially because looking for a technosignature in this like massive amounts of data is just like looking for like a needle in a haystack, like some anomaly in this much larger data set. And machine learning can be great at that sometimes if it's trained well and other stuff like that. But it can do a great job at looking for some weird thing in this massive amounts of other things that look kind of like it.
Yeah, and as I mentioned earlier, we are certainly relying heavily on machine learning, and there are different approaches to do it. For some of them, you have to have some preconceived notion of what you're looking for. For other flavors, like using neural networks, you can just kind of feed in your data and see what comes out, but you might not find what you think you're looking for. Our experience where we measure various properties of these light curves, like how much are they changing? Do they have repeating patterns? And then we feed them into machine learning. It does affect what gets spit out by the machine at the end. So it's certainly by no means perfect. There's a lot of fine tuning that we have to do with our human brains and vetting afterward, but it's definitely a crucial tool when there are just so many stars to look at that we can't really do it unless we get thousands of people to help out, and we would have to train all those people. So
okay, Another question from the public, which is also a question I like to ask. So let's imagine I give you $1 billion. Okay, what will be the space telescope or the telescope that you will build, Anne-Marie, to find for megastructure? What will be the radio antenna array that you will build for technosignatures, Noah? So Anne-Marie, we start with you.
Well, I think I already kind of touched on what I would like, which is a suite of instruments on a telescope. The mission we're working with right now just looks in broadband white light, and we're kind of limited in what we see interesting features in the time domain, but we can't analyze it in real time. So the key is, and the risk is, if we find something interesting and then we go look at it with other telescopes on Earth afterward, whatever we saw might be gone. So we really need a telescope that will look at different wavelengths, maybe has some fancy spectrographs that can look at the stars as we monitor their light at different wavelengths simultaneously. Maybe two telescopes operating in tandem, so they can each look at the same star at once, but we can verify that it's not something that's intrinsic to the telescope. So we really want to look at these stars from a variety of angles, and right now we're just kind of looking from one, and then we're investigating afterward.
So in short, you would like to mass produce tests and send something like 20 or 100 tests in space with a filter wheel in front of them, so you can have different colors as well. That's it?
Yeah, I think that would be great for exoplanet studies too.
Okay. Very good. What about you, Noah?
All right, so you've heard me complain all night about interference in radio data, and I think that's like a lot of radio astronomers would completely agree with me that the radio interference is such a pain with the radio astronomy. And so I think, given $1 billion, I would say let's put a telescope on the moon.
Okay.
Where there is very little to none of this other radio interference. Like, there's no one walking up with their cell phone. You don't really have the satellites as much. Yeah, I mean, I think that'd be great.
Okay, that's a good answer. On the far side of the moon, so it's shielded from the radiation coming from Earth. But it also assumed that we are not going to go on the moon, and we're not going to send rovers over there that's going to start trekking and hiking on the surface of the moon, because they communicate with us by radio. So.
Right. No, I mean, there'd definitely still be a little bit, but I think it'd be way, way better than any radio telescope on Earth.
All right, it will make your life easier, definitely.
Yeah, definitely.
Okay, well, that's a perfect transition for my last question. I mean, this chance of success of this search is kind of small, right? We have to be realistic. Finding technosignatures or finding megastructures will take time. We have to observe a lot of stars to do that before detecting probably something. So what is your personal motivation when you wake up in the morning and you start working on this search? What motivates you? What is the thing that say, okay, I have to do that today? Anne-Marie, you want to start?
Sure. You know, I guess I'm kind of attracted to big rewards that may be out there. Regardless of how risky the endeavor might be, this would be a world-changing thing. And I think in this day and age, you could argue about whether any civilizations we find are benevolent or not, but I do think we need a little assistance here on Earth. And if we could get in touch with more advanced civilizations, they could give us some clues on, you know, how to remove carbon dioxide from our atmosphere, or things like that, how to deal with pandemics. I'm not saying that if we detected a megastructure that we'd immediately be in contact and receiving good information, but it's a step to get there. And I just think we kind of owe it to our own world to constantly be pushing the boundaries and trying to find out what's out there. It's extremely motivating to me just to be searching.
Hey, very good answer. What about you, Noah?
I think so. I feel like one of the biggest questions is like, does extraterrestrial life exist out there in space? And for me, answering this question is like the motivation. So like I wake up in the morning, I'm like, what if today is the day that we just discover extraterrestrial intelligence? And like that would be so, so awesome that like it just keeps me going.
All right. Will be so awesome. It will change the world and help us to find an answer to some of the important questions we have at the moment. And to summarize your
Definitely.
thought, right?
Yes.
Okay.
Yeah. Yeah.
Well, thank you very much, Anne-Marie and Noah, for this interesting conversation and for telling us about your work. And I see that Bill reappear magically on the screen. So Bill, is all yours.
Great. Well, that was awesome. That was terrific. And, looking at the questions in the Q&A, there were some brilliant questions. They're really good questions. And of course, I'm sorry we couldn't get to them all, but it's good motivation for you to come to the next SETI talk, which is going to be nothing but questions from you to us. So we'll have much more time to delve into some of them. So please come back in June for the Ask Us Anything session, and you'll have a chance to dig into those. Some of the questions that were asked, I've got a couple of answers to. There was a question about, for example, ground-based telescopes being used for technosignatures, while not for megastructures of interest to Anne-Marie in particular, and Noah. They are being used to, for example, look for laser pulses. So there's a SETI project at the University of California in San Diego, and there's our own laser SETI project at the SETI Institute, where we are using ground-based optical telescopes to look for laser pulses. Somebody asked about, well, what, could people see that kind of phenomena if they were astrobiologists and SETI researchers on other planets looking at Earth? Not too far from the SETI Institute in Mountain View, there's the world's most powerful laser at the Lawrence Livermore National Laboratories. And that is so bright that if you couple the output of that laser, bounced it off one of our, say, 8-meter telescopes on Earth and shined it out into space, it would outshine the sun by a factor of 10,000 times. So in terms of how far away can alien civilizations see our star, they could more easily see a laser pulse like that. And what is a technosignature? I think a monochromatic pulse of laser light, for example, if it was determined and validated to be from outside of our solar system, that would be a pretty indisputable technosignature. And because nature doesn't produce such phenomena. And more interestingly, if it was modulated in some way that it seemed to contain information, even if we couldn't translate or understand what that was, that would be even further indication that this is technology, and technology as a proxy for life and intelligence, I think, is more interesting than, say, biosignatures that the James Webb Telescope might be looking for in planetary atmospheres, because biosignatures might be indicative and suggestive, but not necessarily definitive. You find a technosignature, and that's like game over, folks. We are not alone, and there are advanced civilizations out there that we've just discovered. And of course, a narrowband radio transmission, and again, particularly one that was being modulated in some way that seemed to contain information, and particularly if we could validate that it was coming from outside of our solar system, pretty much a slam dunk that that's an undeniable and irrefutable technosignature. So there are interesting ways. What about people looking at us, at our planet? We talked about Arecibo. Arecibo, when it was up and functioning before it collapsed a year or so ago, more than a year ago now, I guess, it had the world's most powerful radar transmitter, a megawatt transmitter that was used by NASA, among others, to look at and study asteroids. That's the brightest thing that we have on Earth. That would be detectable even with Earth-like radio telescopes from probably as far as 100 light years away, depending on the instrument. So our presence could be known, but think about how far our technology has gone in time and therefore in space. We've been transmitting in radio and television and broadcast very low energy and not in any one particular direction, but we've been doing it for about 100 years. So our technosignature has an envelope now that's about 100 light years from Earth, which, as Frank mentioned, in the context of a galaxy 100,000 light years across is not very far, but hey, it's something. And really interestingly, if astrobiologists were looking at the Earth's atmosphere, and particularly doing it over time, and noticing how greenhouse gases carbon dioxide, methane, and others were increasing at an exponential rate in recent years. That would also be a technosignature. Anne-Marie talked about, James Webb and scientists interested in looking at signs of technology in terms of weird chemical formations that nature wouldn't necessarily produce in planetary atmospheres. Those could be technosignatures. So technosignatures, do take on a wide range of phenomena. And that's a good example of the more different things we look at and the more different and imaginative the tools we use to do those searches, the more likely we are to be successful. And, we probably have yet to imagine modes of searching for things that we can't conceive of how information would be transmitted, like gravitational waves or neutrinos or other things. So lots of interesting ideas of what SETI is going to look like 10, 15, 100 years from now. Anyway, I digress, and I want to thank you, Frank, and Anne-Marie and Noah, for really an amazing and enlightening conversation. And thanks to all of you out there for all the great questions. I'm sorry we couldn't address them all, but I always like to say that unanswered questions are actually opportunities for you for your own further investigation. So if we didn't get to your question, you could see what you could do to answer the question with kind of your own research. So think about that and that opportunity. We did reach a global audience. Again, today we had guests from more than 27 different states and more than 11 different countries. We were joined by friends at the Robeson Planetarium in North Carolina, the Phoenix Astronomical Society in Arizona. We had folks joining us from our neighbors at Stanford University and down there at Texas A&M. In fact, our Texas A&M guest claims to be a part-time human, which raises all kinds of interesting questions. And one guest claimed to be from a distant planet where they consider Earth to be an exoplanet. So that's very cool. If you can give us your coordinates on the celestial sphere, we'll try to make contact with you. Great to see so much interest in our signature research, looking for signs of technology beyond Earth as a proxy for life and intelligence. And again, this worldwide community proves that curiosity unites us all as human beings, regardless of our language, gender, race, ethnicity, or indeed, regardless of our intelligence being natural or augmented. We had people from Colorado, Florida, Arizona, New York, Texas, New Jersey, California, loads from here, Tennessee, Montana, North Carolina, Connecticut, Minnesota, Louisiana, Michigan, Nevada, Illinois, Hawaii, South Carolina, Virginia, Georgia, Washington, Oregon, Pennsylvania, Indiana, Oklahoma, Wisconsin, and Delaware. And lots of friends from Canada and others from Poland, Hong Kong, several from India, Puerto Rico, New Zealand, Argentina, Sri Lanka, Guatemala, Mexico, and Ecuador. So very cool to have so many people from all over our planet joining us today. And if I didn't mention your location by state or country, that's because you didn't tell us. So next time, don't be shy. And if you have curious and inquisitive friends in distant lands or states we didn't mention, let them know about SETI Talks, and let's bring even more people together from across the world in the name of science and curiosity. Before closing today's discussion, just a reminder that SETI Talks is a production of the SETI Institute in Mountain View. We are a nonprofit research and education institution, and our mission is to lead humanity's quest to understand the origins and prevalence of life and intelligence in the universe, and to share this knowledge with the world. And our SETI Talks lecture series is supported in part by donations from the public, from friends of science like you. We bring these lectures and other events to you at no cost, but we're very grateful for any and all donations that allow us to continue bringing the stories of extraordinary science and exploration to you. So you can visit us at SETI.org for more information. You can sign up for our monthly newsletter we call Journey. Make a donation if you're so inclined, or just peruse our website, which is full of lots of fascinating and compelling content. So thanks again to all of you for being with us today. Thanks for today's moderator, Frank, and our guest speakers, Anne-Marie and Noah. I also want to thank Rebecca, Lee, Jasmine, Beth at the SETI Institute to make the SETI Talk series possible. Don't forget to visit our YouTube channel as well, where all of these talks and lectures are recorded, and you can tour all kinds of lectures and presentations and programs that we have on our YouTube channel. The work we do at the SETI Institute is for all of humankind, so don't just stand by and watch. Come and join us at SETI.org and get involved. The search for life beyond Earth is a journey of ultimate discovery, and we invite you to come along. Thanks for being with us, and please join us again on June 29 for our Ask SETI Anything special event. So good night and see you next time.